Hey guys, so we're on slide 13 of chapter 16 PowerPoint. We're talking about strong and weak acids, and essentially we need to kind of define a little bit better what a strong acid is versus a weak acid. So in water, when two water molecules crash into each other, we form hydroxide and hydronium. Hydronium, H3O plus, is the acidic part of water. H3O plus is an acid. Okay, it can give a hydrogen away and turn back into the water molecule. So essentially, if I put an acid into water, like HCl, if it wants to give its hydrogen away, it has to give the hydrogen to a water molecule, which turns that water molecule into H3O plus. Okay, but H3O plus really wants to give the hydrogen back to the HCl molecule, because neither one of them wants it. They almost are playing like hot potato with the hydrogen, trying to pass it back and forth. Okay? Well, if the acid that I've added, if it's a stronger acid than H3O, that means it's better at giving the hydrogen away. So what happens is, with a strong acid, it is so strong that when it gives the hydrogen to the water or the H3O is unable to give it back. Okay, so the acid is going to stay in the dissociated form. I'm going to end up with a lot of H3Os floating around because every acid molecule is going to give away its hydrogen and cause a H3O to be formed. Okay, now if I put a weak acid into water, a weak acid is not as good at giving its hydrogen away, and when it gives it away to the water, the H3O, if it's stronger than the acid I've added, then it's just going to give the hydrogen back. So what happens with a weak acid is that most of the molecules of the acid, they're unable to get rid of their hydrogen and keep it away. Every time they try to give it away, it just comes right back. So most weak acid molecules stay in their associated form. They stay together. Okay? Because H3O plus is a stronger acid than the acid that we put in there. Okay? So that's the technical difference between what a strong acid is and what a weak acid is. It's kind of, which way does the equilibrium favor? Does it favor the acid giving the hydrogen to the water, or does it favor the water putting the hydrogen back onto the acid? That's a strong versus a weak. Okay? When we look at bases, we kind of have the same thing. The strongest base that can exist in water is hydroxide. So if we put something in the water that's stronger than hydroxide, then basically like ammonia. If ammonia was a strong base, then every ammonia molecule would walk up to, every ammonia would go to a water molecule, yank the hydrogen off, and turn all the water molecules into hydroxides. Okay? Ammonia is not good enough to do that, though. Every once in a while, a ammonia molecule will be successful taking hydrogen from water, but most of them aren't. So most ammonia molecules are going to stay NH3. Only a few will become NH4 plus, which means only a few hydroxides are going to be formed. So that's going to be a weak base versus sodium hydroxide is a strong base. Whatever number of molecules I put in there, when it dissociates, I get lots of hydroxides floating around, so that's a good strong base. Now, one more kind of special base, the oxide ion. If I put like sodium oxide in water, the sodium is going to just break off and be a spectator. But the oxide ion, when it bumps into a water molecule, oxide is an extremely strong base. It's going to pull a hydrogen off the water. So the oxide ion is going to, when it gains a hydrogen, it's going to become hydroxide, which is what we wanted to make for a base. But then the water molecule, if I strip a hydrogen off of it, it becomes a hydroxide too. So the oxide ion, when you put it in water, actually forms two hydroxides from each O2 minus that was in there. It becomes one itself, and it turns a water molecule into one. Okay? So that's kind of a special reaction. So a strong acid is going to be an acid that ionizes pretty much 100%. Again, it approaches 100%. I mean, it's not technically every molecule, but it's pretty close to that ionizes. In those cases, if I had put in 100 HCl's into a solution, if they all ionize, that means I'm going to end up with 100 H3O pluses in the solution. It's a one-to-one relationship. So the concentration of the acid is going to equal the concentration of hydronium that I form in the solution. For example, if I have a 0.1 molar HCl solution, if all the HCl's ionize, then the concentration of H plus ions or H3O plus, remember we can switch back and forth between those, but the H plus concentration will be the same, 0.1 molar. That's going to be important for calculating pH when we get to that part. Okay. Now, in the beginning of the second PowerPoint, we're going to show that reaction in the form of an ice table to prove why the initial concentration of the acid ends up becoming the H plus concentration. It's not a complicated thing, but we will show it because we want to show the difference between strong acids and weak acids and how we approach the math of the calculations. So, if we have a weak acid, they are going to only ionize a little bit. It's usually significantly less than 100%. Most weak acids will actually only ionize probably between 0.1 and 5%. It's a very low value. So the number of H pluses I get are going to be a lot less than the original concentration. So if I had 0.1 molar acetic acid, the H3O concentration is going to be a lot less than 0.1 molar. It won't be the same. Okay? All right, bases. Same idea. Strong bases will completely ionize to form an equal number of hydroxides to whatever the base concentration is. So if I put in 0.1 molar sodium hydroxide, then that's going to make 0.1 molar hydroxide. If I look at weak bases, they only ionize a small percentage. So the concentration of hydroxide in the solution is going to be a lot less than the initial concentration of the base. And therefore, that's going to affect our calculations. Those calculations are going to come up in the second PowerPoint that we do in a little while. So we need to memorize our strong acids and bases. First of all, our hydrohalic acids, our strong acids, that's HCl, HBr, HI. A note though, hydrofluoric acid, HF, is not one of those. At the end of chapter 16, we'll talk about why some acids are strong and why some aren't. But for now, we're going to memorize the strong acids so that whenever they come up, you know how to handle the calculations, because strong acids and weak acids are calculated differently. So the hydrohalic acids are strong acids except for HF, nitric acid, perchloric acid, sulfuric acid. Now, with sulfuric acid, it's important to note only the first hydrogen comes off as a strong acid dissociation. The second hydrogen is more like a weak acid, so it has to be dealt with separately. Again, we'll talk about that when we get into a later slide, but just remember with sulfuric acid, if it's 0.1 molar sulfuric acid, the hydrogen concentration still ends up being around 0.1. We don't factor in the 2 in the formula when we calculate the H+. Okay? Again, we'll explain that better at a later point. And then all of those are stronger acids than hydronium. Then we have our strong bases. Those are group 1 hydroxides, the bottom of the group 2 hydroxides. Any metal oxides that we put in, again, we talked about that's kind of a special one, but those are our strong bases. Again, our weak acids and bases are going to be anything that's not on this list must be either a weak acid or a weak base. All right, so then we also talked about our conjugate pairs. So this slide kind of shows our strong acids are at the top on the left, HCl, sulfuric, and nitric. This is not a complete list, but the 3 at the top are strong acids. They're all above H3O. Then everything beneath H3O, those are weak acids. The further down you go, the weaker they get. So these are in decreasing order. But then when I look at the conjugates of each one, so this acid, if it loses a hydrogen, its conjugate would be carbonate. If this is an acid, this is a conjugate base. The strength is inverse. So with my acids, the lower down the acid is, then when I look at the conjugate, it's going to have a stronger conjugate. A really weak acid has an extremely strong conjugate base. A really strong acid is going to have an extremely weak conjugate base. So if HCl is a strong acid, then Cl minus is an extremely, extremely weak conjugate base. All right, now, calculations. We're about to get into all the section. The rest of the chapter is primarily going to be about calculations. Number one, if we want to assess how acidic a solution is and actually put a number value on it, we tend to use the pH scale. That's something that everybody has heard of from previous classes, whether it's biology or geology or high school chemistry or whatever. The pH is the negative log of the hydronium concentration. That is our fundamental equation that we have to know more than anything else. We have to be able to calculate the pH in this chapter and the next one. Now, there is another scale that is less commonly used, but it's still going to be important for us because the way we do our calculations, there are going to be times that instead of calculating the pH directly, we're going to calculate the pOH first, okay? So, anytime I put a little p in front of something in this section, it's going to stand for the negative log. So pH is the negative log of the hydrogen concentration. pOH is the negative log of the hydroxide. Okay? Later, there will be something called a pKa value. Well, the p just means negative log. So if I say pKa, that means the negative log of the Ka. If I say the pKb, that means the negative log of the Kb value. If I say p-nut, that's the negative log of a nut. That's a joke. All right, move on. So in water, we previously established that the H3O concentration in pure water is 10 to the minus 7 molar. That was just based off the autoionization of water that we did earlier. So if I take that concentration and do the negative log of it, that's going to give me that the pH of pure water is 7. Now, in pure water, the H3O concentration and the OH concentration are equal. So essentially what we're saying is that a pH of 7 is a neutral solution. Now, as the hydrogen concentration goes up, when you do the negative log, the pH is actually going to go down. Okay? A high H plus concentration, which corresponds to an acidic solution, is going to have a pH below 7. The other scale, if I know that H3O is 10 to the minus 7 in pure water, the hydroxide is also 10 to the minus 7 in pure water, because remember, in pure water, they're equal to each other. So if I took the negative log of that number, that's the pOH, I would actually get the same value of 7. And then there's another relationship. The pH and the pOH are always going to add together to give me 14. So right now, in pure water, the pH and pOH are 7 and 7. 7 plus 7 equals 14. If the pH was 4, I know the pOH would be 10, because 4 plus 10 makes 14. Okay? So that's another equation that you want to know. Again, all these little equations, when you work through problems, you're going to have to kind of work your way from one thing to the next, to the next, to the next. We have to know how to calculate pH and pOH. We need to know the relationship between these two. We also need to remember the equation Kw equals H plus times OH minus. And if we know all those equations, then that's going to allow us to calculate several different things that we need to know about each solution we look at. So there's my last one. The pH plus the pOH equals 14. That is always true at 25 degrees Celsius when the Kw equals 1 times 10 to the minus 14. For the most part, we're always going to assume that's what we're dealing with. Now, in mastering chemistry, there are a couple of problems where they'll ask you to find Kw or find the pH or something like that at a different temperature. And then some funny stuff can happen at that point because this equation might change slightly. Again, on mastering chemistry, just kind of figure it out or ask questions. But normally in class, we're going to stick with 25 degrees Celsius, which means that all these equations are going to work out this way every time. All right, so when we are looking at pH, kind of important just to apply things that we do to everyday life. So here I have a scale of just common things that we encounter in our everyday life, that solutions that are either acidic, basic, or neutral. So when I look at this, at the top, I actually have low pHs. So like your stomach acid is gastric juice, lemon juice, orange juice, any kind of fruit juice is always acidic. Coffee is acidic. Bread, if you take bread and dissolve it in water, it gives you an acidic solution. So there are lots of things that are acidic. Anything that's very sugary or contains a lot of fat has fatty acids in it. Those tend to be really acidic things. Most junk food is acidic. Okay. Then on the other hand, when I look at things that are basic, a lot of cleaning fluids, like sodium hydroxide is a major component in lye solutions, or like Drano, bleach, ammonia, milk of magnesia. Those are all basic things. And then when we look at in food, green leafy vegetables, broccoli, lettuce, and things like that, they tend to be basic. And then essentially, there is a diet out there called the alkaline diet, where if you break down foods into either acidic or basic properties, the ones that are basic properties tend to be much healthier foods, and your body processes those foods in a much better way. So it's not a bad breakdown of what foods you should eat or shouldn't eat. All right, so here are all the equations that we've learned. Up at the, let's see. First of all, starting on this side, this is basically my equation. Kw equals the H plus times the OH minus. And essentially, I've got H plus, I've got OH minus. If I know one of them and I want to find the other one, then I would plug into that equation and solve. I plug the one in that I know, solve for the one that I don't know. So that's the equation that connects these two values to each other. If I take the H plus and do the negative log, it gives me the pH. If I do the negative log of the hydroxide, it gives me the pOH. And then if I go from the pH to the pOH, I know that if I add them together, it equals 14. So essentially, there are 4 different values here that we can calculate about a solution. And there's a simple equation that connects all 4 of them. Okay? So essentially, like, let's just say if I gave you the pH of a bottle of lemon juice, let's say the pH was 2.5. I might ask you to calculate in that solution what's the H plus concentration, what's the hydroxide concentration, and what's the pOH. And you, like, if I give you the pH as 2.5, you should be able to work your way around this square to find all the other numbers. So let's try it. If I have a solution, what's the pH of a solution? If the H3O concentration is 1 times 10 to the minus 6 molar, well, you need to know that if you're given the H3O concentration, you do the negative log of the H3O concentration to equal the pH. If you do that on this one, the negative log of 1 times 10 to the minus 6, the pH should come out to be 6.0. Okay? Now, one more thing about just kind of the things that you have to encounter with mastering chemistry and those things. Significant figures. When we do logs, the rules for sig figs are different. Okay? Essentially, the way the rule works, your concentration that you're given, if it has 1 sig fig, like this one does, the one in the front, that's my only sig fig that I have here. If there's only 1 sig fig, when I do the negative log, the result of a logarithmic function, the sig figs are the numbers after the decimal. The numbers in front of the decimal actually don't count as sig figs when you take the log. Okay? So if I have 1 sig fig in my concentration, that means I should keep 1 decimal place in my pH. All right? You need to remember that, because what will happen, let's say you do you have an H3O concentration that's really tiny, and when you do the negative log, if you get a pH of like 12.45, a lot of times students will think that if there's 2 sig figs in their concentration, then they'll round the pH to 12. Well, if you round a pH of 12.45 to a pH of 12, that's a significant change. Because remember, with a logarithmic scale, the difference between a pH of 12 and a pH of 13 is actually a factor of 10. A logarithmic scale, every unit you go up is a factor of 10 in the real value. So rounding 12.45 to 12.0, that's a significant rounding that's going on, okay? It's not just cutting off 0.4, it's actually losing half of an order of magnitude. That's a big deal, okay? So try to remember that rule so that when you're on Master in Chemistry and all that kind of stuff, if you just cut off all your decimals, you're always going to, it will often make you miss the problem. All right, so what's the pH of a solution if the hydroxide concentration is 1 times 10 to the minus 6? Okay, so this is a different problem. I don't know if I flipped the slide. Now we're doing hydroxide is given, and I want the pH. I'm going to go back to this slide. Notice, like on the first problem we gave, they gave me the H plus, and I wanted the pH. I only did one calculation. I did the negative log of the H plus to get the pH. But now they gave me the hydroxide concentration. They want the pH. I can't get straight there in one step. I either have to go up and over, which would be 2 steps, or I can go over and up, which would be 2 steps, okay? So to get from the hydroxide to the pH, I have to go through 2 steps. Now, the easiest way to get from here to here actually is to go across and up, because if I do the negative log of the hydroxide, that gives me the pOH. And then I just have to do 14 minus the pOH to get the pH. That's a much simpler calculation than the 2 that are over there, so that's kind of the preferred method. So that's what we're going to do. We're going to do the negative log of the hydroxide to get the pOH, and then do 14 minus that to get the pH. So if I do negative log of 1 times 10 to the minus 6, the pOH is going to be 6.0. Then do 14 minus 6.0 to give me the pH, which is 8.0. All right, finally, what are the pH, the pOH, and the hydroxide concentration of a solution that has an H3O concentration of 0.025? So again, I gave you on the square slide, I gave you one value from one corner, and you have to find the other 3. All right, I'm going to let you work that yourselves. The answers are given here, so just come to class and ask questions if you need to. That is the end of the first PowerPoint for Chapter 16. The next video will pick up on the second PowerPoint.